Let's finish first the example that we were working on last lecture. So we had a computer or a car which had a problem. We took it to an expert for a fix. The expert had two strategies. Let me just write down what we exactly had last week. The expert could be honest or dishonest. The consumer could accept or reject offer. The price of the expert and the payoffs that we had. I'll go fast over them. So pi minus r e minus 1 minus r I. If the expert was honest and the consumer rejected, then the payoffs were 1 minus r pi for the expert minus r e prime minus 1 minus r I prime for the consumer. And if the expert was dishonest and the consumer accepted the price, then the profit of the expert was r pi plus 1 minus r pi prime, and the profit, the payoff of the
Because even though it rejects being
So here, the consumer rejects the offer. If he rejects the offer, he goes out for the outside option. With probability r, the computer has a major problem, and the outside option will cost him e prime. With probability 1 minus r, the computer has a minor problem, and the cost of the outside option for a minor problem was?
You said that if it costs a minor problem, then he will accept, even though it's not.
Oh, yes, I'm sorry. Yeah, that's what we, I was rushing. Yeah, so if it's so if that's what we said. Rejecting meant rejecting a high price. Sorry, thank you for fixing that. What did we write last week, I hope? Okay, so last week we had it correct. Now I was rushing, I didn't pay attention to what anyhow. Okay, thanks, thank you. So if he was, if the expert was dishonest and rejected the offer, so when the expert is dishonest, then he will always say it's a major problem. So in that case, the consumer will reject. So the profits will be 0 for the expert minus r e prime minus 1 minus r I prime. Now it takes the outside option. Okay. So that's what we had. So from last lecture, I didn't write this. So what was that? That was minus E. Okay. So last lecture, we looked at the best response of player 1, the expert, that's what we had. Looked at the best response of player 2. So that's E was smaller than E prime. Those two numbers are the same. So because of the negative, that's the best response of player 2. And here we had question marks, if I remember correctly. So what did we have? If minus E was greater than minus R E prime minus 1 over R I prime, so let me write that. So actually, let me write it in this case. If E, get rid of the negative signs, is less than or equal to R E prime plus 1 minus R I prime, then dA is a Nash solution for this game, and actually even in the mixed extension game you can show that it's a unique Nash equilibrium. Of course we didn't show that, but it's a simple exercise. So we were looking at the case when R prime. So we did the calculation. We started, I'm not going to do everything. We started by assuming both H and D were in the support. And then from that, by the way, we called the probability that the consumer will accept, we denoted with Q. And hence the probability that the consumer reject, we denoted with 1 minus Q. The probability that the expert would be honest, we denoted with P. Hence, dishonest with probability 1 minus P. So from here, we found out that Q star was equal to pi over pi prime. Let me write those two. So when constructing the model, we assumed pi prime is greater than pi, and we assumed that I was less than I prime was less than E was less than E prime, right? Those are the assumptions, and all of them, of course, positive. Okay, that's what we had. So because of that, that's a number between 0 and 1. Hence, both A and D are in the support. Using that fact, we found P star, or just Q and P. So what did we write last lecture? R, E prime. Sorry? With the R, E prime? Okay, yeah, sorry. Minus E. I prime divided by 1 minus R I prime plus R times E. So let me write that as minus 1 minus R E. Okay? So that's 1 minus R I prime minus E divided by R E prime minus E plus 1 minus R I prime. Of course, to make sure that everything is right, I have to make sure that this is a number between 0 and 1. So at the end in the rush, I said, well, if I replace this with E, R E minus E plus 1 minus R I prime will have in the numerator. And because we're replacing E prime with a smaller number, we said this side, the left side, is bigger than the right side. And then, we had 1 minus R I prime minus E. And actually, the numerator and the denominator are the same. So I canceled out both sides and got 1. So it looked like this was bigger than 1, which was a mistake that I made in the rush. Well, this number is definitely bigger than this number. So when I divide both sides with 1 minus R times I prime minus E, what happens? The sign changes. You see, whenever you're multiplying both sides of an inequality or dividing both sides of an inequality, you have to pay attention to the signs. I prime is less than E, so actually this number is negative. So if I divide both sides by a negative number, the direction of the inequality changes. Hence, this number is less than 1. Okay, and together with this assumption, okay, that's what we were looking, this number is bigger than 0. Okay? That's what we had. Move it over here, it becomes 12. So this P star is a number between greater than 0, less than 1, which implies that both H and D are in the support of the mixed strategy of player only. We completed the circle. So, yep. Did I make? Oh, I wrote the same thing again. I'm sorry. Yeah, I'm having problem with the negatives. So usually when I write things, I try to get rid of the negatives, which is always a good idea because you keep making mistakes. So yes, this number should be negative because the denominator is also negative. So the ratio, yeah, we take the negation of that. Thank you. Okay, sorry about that. Okay, anyhow, so P star Q star is a Nash solution of the mixed extension game. And, you know, with a little work, I will not do that. We can easily show that this game does not have any other mixed strategy. So you assume that only H is in the support. Show that that leads to a contradiction. Only D is in the support. That leads to a contradiction. I will not do that. I'll leave that as an exercise to you. Sure. Uh-huh.
It doesn't have a Nash. Can you say that?
So, sorry, come again?
It doesn't have a Nash.
If this is the case, the pure strategy, the original game does not have a Nash equilibrium. Or to take it in another way, there's no pure strategy Nash solution.
In the mixed extension, also it will not have a Nash equilibrium when only one strategy is in the support. For example, considering that only H is in the support or only D is in the support of B. Because it doesn't have a Nash equilibrium in the pure strategy.
That, would that have to be the
No, I don't think
case? So, you have an example in mind?
I don't have an example in mind, but it could be the case that the support for the first player is only H, and the support for the second player is 2. So that would be a mixed extension. That would be a mixed.
So your friend has an, what she has in mind is the support also only has T, but the support only has, both has left and right. So for,
It has on left and right, and the payoff when T's played should be equal.
sorry,
The payoff
yeah,
of player 2 should be equal.
the player
None
two,
of them should be Nash solution, or if none of them is Nash
Uh-huh.
solution, then T cannot be in the support.
if none of them is the Nash solution, so if T is in the, let me try to construct a simple case. If we have a case like this, the expected payoff, so T is not a, will not be a Nash solution. Oh, it will be here. I don't want that.
What would be the case if both of them have the
Well-
same payoff? And that would be what we
So if I can put it something, I don't want that. And I don't want, well, let me think about it. I don't know off my hand. At least we don't have any theorem which directly verifies it, but you do have a point, but I have to think about it, okay? So let's finish with this. The reason why I chose this example is that to show you that, you know, most of the time people prefer to work with numbers rather than variables, parameters, okay? Working with parameters when you're constructing models, even if you can put numbers, you know the value of the parameters for a specific game, it's always a good idea to work with variables, okay? So once you're done with the modeling, then you can do some comparative statistics. You can ask, what would happen if, for example, the likelihood of a major problem increases? How would the equilibrium change? Okay. So as R increases, what happens? First of all, well, Q star doesn't depend on R. Again, we're assuming that it changes, but it's still between 0 and 1. I didn't write that, but we also assumed R is bigger than 0, but less than 1. Okay? If it's equal to 1, this doesn't make sense. Okay? So we increase R. What happens? Well, it looks like the likelihood of the consumer accepting the offer, the price, doesn't change, which initially looks a bit strange, kind of, right? But let's look at P star. What happens to P star? Well, so we're looking at what happens when R increases. According to our analysis, Q star does not change. Okay. Well, if you take the derivative of this with respect to R, I will not do the mathematics now. What you will see is it decreases with an increase in R. Actually, even before that, before taking the derivative, I should have asked, what do you expect would happen? If the probability of a major problem increases, would the expert be more honest more frequently or dishonest more frequently? What is your guess? What does your intuition say? Dishonest. If the probability of a major problem increases, your friend claims that P star would decrease. That is, he will become honest less frequently and hence dishonest more frequently. Okay. So first of all, the mathematics tells us that that is the case. But again, this is not just mathematics. We're doing economics. We have to find at least some kind of intuitive explanation to it. So you as a consumer know that whenever you have a problem, the likelihood of it being a major problem has increased. Okay? So you would, whenever the expert tells you that it's a major problem, what would your reaction be? For most of the people, it would be to believe the expert's opinion, right? Because it's something which happens very frequently. So when the expert tells me that's a major problem, I would be more tempted to believe him. Okay? No? Okay, so but then that analysis hasn't finished. So I would be more tempted to believe him. Well, the expert knows that I would be more tempted to believe him. So what will happen? He would be dishonest more frequently. Okay? But then I will also guess that he would be dishonest more frequently, which will counteract my initial belief. Okay? So on one side, when he says, okay, so I have two sides on my shoulders, it's one economist tells me that, well, such problems are very frequent, so if he tells you that it's a major problem, you should believe it. That tells me that I should increase Q star. But on the other side, well, the expert knows that you're going to be accepting more frequently, believes that you're going to be accepting more frequently. And so what would he do? He would lie, be dishonest more frequently, which would make me think that I should believe him less frequently. The thing is, these two effects cancel out. Okay? But there's nothing to cancel this out. So as R star increases, P star decreases, no change in Q star. The mathematics tells us that, and intuition also tells us that. Okay? So that's why it's usually, even if the problem is given in a numerical format, I strongly recommend that you try to solve it in a parametric format so that you can analyze what happens when some of the parameters changes. Make a habit of that. Okay? Most students have a habit of replacing everything with numbers because it's easier to work with. There's less symbols to carry around. Things cancel out, add, subtract, multiply. You know, you will not have 2 R times E prime. You would have a single number here, which would make the arithmetic easier. But then at the end, you will not be able to do comparative statistics. You will not be able to check if your answer is correct or not, and so on. Okay? So what I would recommend is, well, we have the parameter E prime. What would happen when E prime changes? For example, increases. Okay? Or decreases. Okay? What would happen if E changes? What would happen if pi prime changes? Okay? Do it both mathematically. So if pi prime increases, that is the profit the expert gets when he charges a high price to a minor problem. Q star decreases, but P star doesn't change. So mathematically, that's what it says. Try to find an intuitive explanation to it. Okay? You have to have a strong mathematical background, and you have to have a strong intuition. The mathematics should enable you. The intuition should give you ways to check your results. You know, they should support each other. Okay? Any questions? Any questions? I will not do that check, but you know, check what happens when E prime increases. Check what happens when pi or pi prime increases or decreases, whatever. Okay? Both mathematically and intuitively. I'll leave that as an exercise to you. Any questions? Okay. Then I'll go into a new topic, correlated solution concept or equilibrium. Okay. So for that, let's go back to our battle of sexes game. Actually, I would have preferred to use the traffic crossing game, but I was at homework, so I'll keep it for later. So battle of sexes, we had 2 options. Was soccer or opera, and the payoffs were, the Bernoulli payoffs were as follows. Okay, so in this game, we noticed that there was 3 Nash equilibria of the mixed extension game. And those were, I'll write only the first components of the mixed strategies. So that was 1, 1. Both go to the soccer match. 0, 0. They both go to the opera. And then it was 2 over 3, 1 over 3. Okay, I just wrote the first components of the probability measures. Okay, so first player selects soccer with probability 2 over 3, opera with probability 1 over 3. Second player selects soccer with probability 1 over 3, opera with probability 2 over 3. Okay? So those were the Nash solutions. So which one would result in this game? Well, that's where the Nash equilibrium stopped. It says these are the possibilities. You know, depending on the culture, depending on various things about the players, one of these would happen. Okay? Now, these two players, before they play the game, these couple, man and wife, you know, in the evening, they're soccer. This will tell you how much I know about soccer. Soccer matches are usually in the evening, right? Yes, okay. That tells you how much I'm interested with soccer. But so in the evening, the couple is either going to meet, you know, is going to go to a soccer match or an opera. Okay. So what they do is before they go for work, they talk. So they pre-communicate. They communicate before the game starts, but they cannot make any binding agreement. So they can talk and they can say that after, you know, work, we'll meet at the soccer match. Okay. So after work ends, player one does not have an incentive to go to the opera because he believes that player two, his or her husband or wife, will go to the soccer and vice versa. Okay? So this will be a self-enforcing commitment. Even though they could not sign any binding contracts, they just talked about it over breakfast, went for work. Okay? If they agreed before they left for work to meet on the soccer field, that's what will happen. Okay? But this situation where player one goes to soccer and player two goes to opera is not a self-enforcing agreement. That will not happen. If player one thinks that, you know, they agreed that at breakfast, player one said, well, I'll go to soccer. Player two said, I'll go to opera. Okay. Well, after work, player one would think, well, she's going to the opera. That's what she said in the morning, even though we didn't sign a contract. Then what is best for me to do? To go to opera too. So this is not a self-enforcing agreement. Okay? So by pre-negotiation, pre-communication, okay, even though they can't sign, you know, well, we assume that they can't sign any binding agreements, otherwise the structure of the game would change. Okay? All these cases would be self-enforcing agreement. So they could agree on saying that, well, to put 3 marbles in a bag, okay, and after work, select one. Let's say that 2 white, 1 black marble, okay. Then player one will say, I'll select a marble at random, okay. If it's white, I'm going to the soccer match. If it's black, I'm going to go to the opera. A similar thing for player two, okay. So they could make such an agreement, okay, which they would end up here. Again, this is a self-enforcing agreement, okay, even though they haven't signed any binding agreements, okay, contracts. That's a self-enforcing agreement. Well, if they can agree on something like this, why not let them agree on something more sophisticated? Okay? Rather than selecting something at random, each separately, why not observe something which happens randomly, but something which both of them observe? So, for example, it's springtime. The probability that it's going to rain this evening is equal to the probability that it's going to be clear this evening. Okay? So they could say during breakfast, well, if it rains, let's meet at the opera. If it doesn't rain, let's meet at the soccer match. Okay? So that's some random device, the weather. And what they do is they correlate their actions based on the result of this random device. Okay? Okay? So that's the idea behind correlated equilibrium. Okay? So can they design a random device, okay, that will enable them to coordinate their actions, and no agent will have an incentive to deviate from those actions. Okay? So let me give you the formal definition. Given a game gamma, I'm using numeric representation for preface, and again, because of the randomness here, I will have to talk about expected payoffs, and hence, we're assuming that the numeric representations are Bernoulli utility functions, Bernoulli representations, okay? So, a probability measure. Actually, before that, there are two ways I can define correlated equilibrium. One of them is mathematically a simple way to do it, but it's less realistic. The other one is a more realistic way to model correlated equilibrium, but it's mathematically more sophisticated. Which one do you want to start with? The mathematically simple, the mathematically more complicated? But simple, okay, so let's do it. And then at the end, today we will not have time, but later I'll give you at least some idea about the mathematically more complicated, but the more realistic way of defining it. A probability measure I'll denote with mu hat. That's a probability measure on S. Okay, that is on the set of all strategy profiles. Unlike the Nash equilibria, we had a list of probability measures, and the first probability measure was on a probability measure on S1, the second one a probability measure on S2. Here we have one probability measure, which is a probability measure over the set of all strategy profiles. Okay? Is a correlated solution of gamma if and only if the following holds. I'll write that in pieces. So what happens here is that some random event occurs. So it's sunny, which signals player one that he should go to the soccer match. Okay? And it signals player two that he or she should also go to the soccer. Well, let's take the first player as female, the second player as male, so that I don't have to say she, every time. Okay? So, okay, and if it's rainy, so a random event happens, it signals the female that she should go to the opera, and it signals the male that he should go to the opera. Okay? But he'll get?
Male gets more utility.
Well, it depends. Not for me. But yeah, that could be also the case. So for many people, so if you like, let's change it like this. Okay. Let's make it like that. So what happens, you get a random event happens, and based on that random event, you're made a suggestion on what to play. Okay? So essentially what happens is that with some probability, you're suggested to play S, and with some probability, you're suggested to play O. Okay? So what player one, let's think about player one. Okay? So he got, the weather is sunny, he got a signal that he should go to the soccer match. Then what does player one do? Well, if this is the signal that I got, what is the signal that my wife got? Okay. In this case, it's easy. I can immediately conclude that she got the signal to go to the soccer match. But that doesn't have to be the case. Maybe this could also be played with some positive probability. The agreement could be such that, okay, if it's sunny, let's go to the soccer match with probability 2/3 and to opera with probability 1/3. Okay? So what player one does is, well, given that I have received, so let's call I, given that I have received the signal SI, what is the probability that my opponent or opponents has received the signal S minus I? Okay. So then what I'll do is I'll multiply that with, well, actually here I can use small minus I. So with this probability, once I saw SI, if I play SI, with this probability, my opponents will be playing S minus I. Okay. And if I sum these up over all strategy profiles of the opponents, what will I find? I will find my expected payoff given that I have received the signal to play SI, okay, and my opponents will play S minus I according to this probability measure, okay, and they follow the signal that they have received. Okay. Or what I could do is, even though I received the signal SI, and even though I believe that my opponents are going to play the profile S minus I with this probability, I could play some other strategy. Okay. And then sum them up. Okay. So this is my expected payoff that I will get if I follow the signal that I have received, the agreement that we have made before. And this is the expected payoff that I'm going to get, or player I is going to get, if player I uses some other strategy rather than the agreed strategy. Okay? So, to have an equilibrium, to have a solution for everybody to behave according to their pre-agreement, what should we have? This number should be at least as much as this number. For what? For every SI prime in capital SI. Okay? So far, so good? Where this is the conditional probability. Yes, so this should be true for player I. So let's go step by step. So player I should not deviate. So we want no agent to deviate. Okay, so far so good? Okay, well, so far not so good. There's still a problem. So we're resolving things one by one. Player I should not deviate. That's what that says. No player should deviate. And what is this? This is the conditional probability measure induced by the probability measure mu hat given SI. Okay? So far, so good? But of course, conditional probability is only defined when? SI would occur with a positive probability. So this thing, I didn't leave enough space, so let me erase this part. You already have that. This thing would be only meaningful if summation mu SI S minus I over is greater than 0. So if this is the case, so which essentially says that agent I should observe the signal SI with some positive probability. If that happens, then we want this condition to hold. Okay? So essentially what happens is that we agree on some randomization device. What the randomization device does is it makes a suggestion on what the players should play. So it says, for example, the example we have, if it's sunny, go to soccer. If it's rainy, go to opera. It's a random device, so it would make the recommendation S to player 1 and S to player 2 with probability 1/2. It will make the recommendation S to player 1, O to player 2 with probability 0. Again, this with probability 0, with this with probability 1/2. So the way to think about this is, again, this is the less realistic way. The other way was more realistic. But then what I would do is I would design a random experiment. Random experiment means I have to tell what are the possible outcomes, rain or clear sky. Okay? So, and then I would say what information does the players get about the outcome of this random experiment? And what are the probabilities of the outcomes? And how are those outcomes linked with their behavior? It's a more mathematically sophisticated model, but it's more realistic. It's easier to understand. But when we translate it here, it's like there's a random device which selects a strategy profile at random and tells each player their component, gives each player their component as a recommendation to play. Okay? So the random device selects SI with some probability. I'm player I observe it. Based on that, I make a guess about what the probability, with what probability are my opponents suggested S minus I. And based on that, I calculate my expected payoff if I follow the recommendation. But I don't have to. There's no binding agreement. I can deviate from the recommendation. And I say, if I deviate from the recommendation, SI was the recommendation, I don't follow the recommendation, I deviate from it. Well, if my expected payoff is not larger by deviating, then I will stick to the recommendation. Okay? So it has the nature of self-enforcing agreement that we have in a Nash solution. But it's more sophisticated. Using some random device, we're able to coordinate our actions. Like if it's sunny, let's both go to soccer. If it's rainy, let's go to opera. Okay, with some random device, we're able to coordinate our actions. Any questions? Any questions? Okay. Well, unfortunately, we didn't have the time to do this example, find correlated equilibrium of this game. But let me, before closing, we can write this in a more simple format. Okay. So if I multiply both sides of this inequality with this number, what would I get here? You would get probability of so what does the Bayes theorem say about conditional probabilities? That's probability of the profile S occurring. So let me write it like this, Si, S minus I, divided by the probability that Si occurs, which is this number. There's the hat here. Okay. So if I multiply the left-hand side by that number, what happens? These cancel. And we're left with the probability that the strategy profile S is selected on the left-hand side, and the same thing on the right-hand side. Okay? So far, so good? Okay. So I can replace this with this, get rid of the conditional probabilities. Okay? Moreover, if this number is equal to 0, well, what this says is that you don't have to pay attention to this inequality. Okay? Well, if that number is equal to 0, what happens to this number? It's going to be 0. And so will this number. So 0 is greater or equal to 0, which means that you really don't have to worry about this inequality. So the whole definition could be replaced with this. Okay, well, let me write this in. Okay, that's the prime there. So you get rid of the conditional probabilities. The one with the conditional probabilities gives you the correct story, the reasonable story, but mathematically it's more complicated. You have to find conditional probabilities. This is easier mathematically, but it doesn't give you exactly what's going on. Anyhow, let's stop here.